Good morning, everybody. I'm excited to present our UTIG seminar speaker for this week, Dr. Eloi Camprubi. His research seeks to unveil how life emerges on a planetary body, design strategies for its detection, and ultimately understand why life as a phenomenon exists. He's a tenure-track assistant professor at the University of Texas, Rio Grande Valley. He's originally from Barcelona, Spain, and he received his master's and PhD from University College London. After that, he did postdocs at LC in Tokyo and University of Utrecht. He enjoys working in an interdisciplinary way and has a joint appointment in UT Rio Grande Valley's departments of both biology and chemistry. Today, he'll be talking about his recent work in the Astrobiochemistry Lab at UT Rio Grande Valley. Thank you.
Thank you so much. You guys can hear me okay? Is that good? Awesome. So yeah, very happy to be here. Thank you so much for inviting and hosting me, and hopefully I'll get to talk to you about my research and what you guys do later today. Yeah, so I just want to talk about rocky wet rocks in space today. The one that we know the most about is Earth. So I'll basically be talking about two projects that are going on in my lab right now. One of them is very much early Earth dynamics, and the other one has to do with other wet rocks in space that are the moons of Jupiter and Saturn within the solar system. So yeah, I'll be talking a little bit about my lab and what we do first. Then we're going to move to talking about what life is as a planetary phenomenon and how astrobiology aims to understand that. Then we're going to go over the first project I'll be talking about today, about the early Earth atmosphere and how that impacts the origin of life. And then finally, talking a little bit about how origin of life and rock-water interactions can actually help direct or help interpret the data that we get when we are exploring these ocean worlds within the solar system, such as Europa, which we sent the probe for about a month and a half ago, Europa Clipper. So yeah, well, I could skip this because I've already been introduced. But yeah, I'm from Barcelona. And so I'm originally a biology and biochemistry bachelor's. And you'll see that now what I do is actually not that close to that. But yeah, back then I was in sunny Spain many years ago. Then I moved to London, to UCL, where I did my master's and PhD with Nick Lane. Then I moved to the Netherlands, to Utrecht University, towards sciences. So that was my first real kind of geo. I learned what minerals are there. Before I was like, yeah, just rocks, right? Then I knew, no, that's not it. And then finally, just kind of briefly and due to COVID, I spent some time in Earth Life Science Institute in Japan, who is a great institute for those of you who don't know, that marries very well biology and geology and physics. It's like a perfect place to study planetary sciences. And yeah, you can call me Eloi, like a metal alloy, or Eloi is fine. I'm used to. So I come from the southernmost tip of Texas, UTRGV. It's the Rio Grande Valley. It's basically all of this connection between Texas and Mexico. It is very hot most of the year. Right now, it's starting to cool off, which is finally it's happening. We are a relatively large university because there's not much competition university-wise down there. We have two main campuses, one in McAllen / Edinburgh, which is where I'm at, like at the center here. But then at the tip where Brownsville is, where SpaceX is, we have another campus. So this one is the Brownsville one, which is the pretty one. And it's kind of all very colonial Spanish. It's really nice. So we have around 32,000 students, a little bit more now. It is the second largest Hispanic serving institution in the USA. So if you guys have like any grant you want to submit and you need to tick a box of minority serving institution, hit me up and we can make it happen. And we are in R2 right now, but yeah, we're going really high. We're going towards R1 status in the next 5 years within. That's what we want. And we have way more grants than we need to become R1, but we don't have yet enough doctoral students being graduated each year. So that's the only thing we need to get there. And we're getting more PhD programs, so it's just a matter of time. So I'm very happy because Elizabeth told me that most of you are not super familiar with astrobiology. Although I was scared that, every time I go and give a talk, I talk a little bit about astrobiology, and I was like, will they be bored by it? Hopefully not. So what does astrobiology is about? Most people think of astrobiology a little bit as the oldest or pre-existing science before, which was known as exobiology. And exobiology was trying to detect extraterrestrial life, right? But after that, astrobiology was born basically by kind of NASA marketing, but now it's its own real non-marketing, not only marketing thing. And so what is it about? It's about, well, according to NASA, it's about understanding the origin of life, the evolution of life, and the distribution of life at a universal scale. So you will see that roughly what I do, it's a little bit of these three things. And many people that call themselves astrobiologists, they work under that umbrella in one way or another. Even though you can be a biologist doing astrobiology, you can be a chemist, you can be a mathematician, you can be a physicist, you can be a geologist, or you can be a little bit of everything, which is a little bit of what happens in my case. So the universe is huge, as you know. This is the 200 billion trillion stars, so it's a lot of stars out there, right? So I don't know how many of you are familiar with the Drake equation, but basically N is trying to quantify the number of civilizations out there that we could establish communication. So not just life, but an intelligent form of life that we can communicate with. And there's a lot of factors here that become really small, like the fraction of planets that have life, the fraction of planets that have life that have developed civilizations, the fraction of civilizations that can send and receive signals in distance. So they become smaller and smaller factors, but because the rate of star formation is so huge, chances are that N equals higher than 1, which means we're not alone in the universe, right? But if so, where are the aliens? Why is alien interaction not a mundane, like Star Wars? You go into Tatooine's canteen and you hang out with the aliens. We don't do that, sadly. So where are the aliens? So people that are astrobiologists like me, we study these questions to basically put some constraints on some of these factors. So for example, one of the things that I care the most about is if there's life within the solar system other than life on Earth, what are the best strategies to detect it? So that basically we can start at least constraining FL, which is the portion of planets that do have life. Right now, we only have one example, which is Earth. So we just need to do better and more space exploration. Although, if N equals 1 and we are alone in the universe, either as an intelligent civilization or as the only living thing, right? Because all life on Earth descends from the same origin of life. We know that, believe it or not. Even if we are alone, that would not be a failure of astrobiology. Some people say, well, the goal of astrobiology is to detect aliens. As if aliens don't exist, astrobiology has failed, but not really. If N equals 1 and we are the only living thing in the universe, that would also be a tremendously important result. It would be very significant. It would probably mean that Earth is very unique and extremely rare and extremely special. So astrobiology is about finding this out, not so much about confirming or not XYZ theories about aliens. So this is a little bit about what keeps me awake at night and why I wanted to become a professor and have my research lab. So again, within this definition, people that work on the origin side, and you'll hear a little bit about this today, even though I'm not going to focus too deeply on it, care about which type of environment life on Earth started. We care about what would have been the sources of organic molecules to build the first cell-like organisms. What would have been the catalysts, the systems that push these chemicals into existence, and the source or sources of energy. Is it UV light? Is it electricity? Is it just chemical gradients in the bottom of the ocean? Which biological functions arose first? There's this big fight in Origin of Life of whether metabolism is the first biological function that arose or whether it was replication. So we deal with that. And then actually something that everyone wants to do is, can we actually make life from scratch in the lab? Can we just invent a de novo life completely from scratch? So I do a little bit of all of that, more or less successfully. Then evolution. Evolution here meaning more evolution of the biosphere and its host planet, because there's evolutionary biology that studies Darwinian evolution. That does a little bit of that as well within astrobiology, but we care most about how a planet and its biosphere interact. So how can we detect biospheres in other planets? Well, because the biosphere changes the atmosphere of planets, for example. And how does cosmological events like asteroid impacts affect the biosphere in reverse? So this kind of deep interaction between a planet and its biosphere. And I do a little bit of that, although not a lot. And then finally, distribution of life in the universe, right? Right now, n equals 1, we only know of life on Earth. So is there life elsewhere beyond Earth? And we care about different things. So one is, do we have how do we detect aliens unambiguously so that we avoid false positives or false negatives? Before that is, what makes a planet habitable? So a planet can be uninhabitable, which means we don't think any life as we understand it could appear, or if it arrives there via a meteorite, for example, like colonize that planet. But then there's many other environments and planets that we think are very habitable. But some may be habitable, but uninhabited as well. So, and we still need to, that is very important, because when we go and explore these worlds, like Europa Clipper, we need to make sure that we're not gonna seed these planets with our own life, because then it means that anything we can figure out, like when the planet is pristine, we would mess up by basically sneezing all over it, pretty much. And we don't wanna do that. And of course, there's like a big component of that, which is not something I do, but there's plenty of people that work at NASA or funded by NASA that work on like the technology development. And we have Elizabeth and many people here that are great experts on sending rovers and other types of crafts to these planets. So this is my little lab. We call it the Astrobiochemistry Lab because of marketing. But we do a little bit of all of that. We do a little bit of biology, quite a lot of chemistry, and a little bit of astro related stuff. And right now we are 12 people. In spring, I'm hiring a postdoc, which hopefully will help me manage this big troop of people. And right now I have 2 PhDs, 4 masters, and 5 undergrads. And yes, it's a lot, so send help. We are also part of the South Texas Space Science Institute, which we created this year. And we want to start doing plenty of workshops. So stay tuned eventually, probably whenever we organize our next kind of workshop. We want to do it in South Padre Island in the coast. So it's going to be fun. Except there's a lot of sharks lately that will bite you. So maybe not swim. But other than that, it should be fun. I just briefly want to talk about 2 projects that are going on that I'm not really going to be talking about today and their results, because they're still very much ongoing and fall much more on the origin of life. But I just wanted to give you like a little bit of a taste on what type of origin of life we do. So one of the projects has to do with trying to find a bridge between Earth early geochemistry, the chemistry of rocks, water, and gases, and ancient biochemistry. So believe it or not, we know quite a bit about the type of metabolism that was present in Luca. Has anyone heard the word Luca before? The last universal common ancestor, right? So that was a guy that is like our great to the, I don't know, 67th grandfather or grandmother. And the question we have, Luca was not the origin of life. It was already a very well fully fledged cell living in the world of genes and proteins. And there's a big disconnect in origin of life between what that guy was doing and the chemistry at the origin of life. So there is a lot of unknowns about how that chemistry that gave rise to life and the latest universal common ancestor, how connected chemistry, were they doing the same type of chemistry or not really? It was like very alien one world for the other. We assume, and that's like that's one of the big divides in origin of life. We assume a path of least resistance and see if the chemistry that was going on in this biological cell, the common ancestor, was also possible just with rocks, water, and gases. It's not at the same level of complexity, but in analog terms. So essentially, we work, so this is greigite, which is a mineral that we find on early Earth at the bottom of the ocean. It's an iron sulfur mineral. And this iron sulfur mineral has these atoms of iron and sulfur and nickel that are basically very similar to these clusters that we find in the proteins that do a very central function for some early organisms. These early organisms are what we call the cetogens and methanogens. They're really small microbes that produce methane and vinegar, okay? And they do that by reacting hydrogen gas and CO2 gas. So it got people that are more clever than me in the past, and they started thinking, well, if these enzymes, these biological amino acid protein-based catalysts, do these reactions using these clusters that are very, very similar to the structure of this mineral that happens in the bottom of the ocean, could it be that this ancient biology arose as a consequence of this geochemistry going on beforehand? So was the bottom of the ocean a giant reactor that was taking CO2, inorganic carbon, and making methane and acetic acid that could have powered the origin of life? So there's plenty of work, and I've worked a little bit about that, of simulating these deep sea vents, these alkaline hydrothermal vents, and simulating all sorts of free energy that is present in these systems because they are extremely out of equilibrium. And in biology, whenever you have an environment that is out of equilibrium, that's pretty cool because it means there's plenty of energy that could be tapped into, for example, making more of your constituent materials. So if you have the origin of life there, it is a great environment to just make more of yourself. And that's what we call biological replication, making copies of yourself. So we are simulating these environments. And right now we're working on CO2 reduction as well, but also we're working on making little strings of RNA, something we call oligonucleotides or polymerization. We take small building blocks of DNA or RNA, our genetic material. We put them under these conditions that are high in energy, and what comes out of them are basically these chains of genetic materials, essentially genes, okay? So we're trying to figure out under which condition genes have XYZ type of sequences, because sequences in genes are the same as information. So we're trying to understand whether this geochemistry, where there's no enzymes yet, can basically give rise to biological information and replication eventually. The way we do this, we simulate the bottom of the sea. So the whole thing needs to be under pressure, even though this system right now, it's only giving us up to 200 bars of pressure, which is not crazy deep in the ocean, but these are some limitations. And basically we make this, so these are syringe pumps that push these liquids, very small volumes of liquids into this little chip, which is a microfluidic chip. And that's greigite, this mineral that I told you that is very important. That's how it looks. It's like this black goo that it hates oxygen, so we need to work inside a glove box. And once they are dry, this is wet here. Once they are dry, we put this kind of shiny metallic thing inside the chip. And then we see if the chemistry here takes over and indeed we're making genes. We use several types of analytical instruments such as LCMS, liquid chromatography mass spectrometry. We also use X-ray diffraction to study the minerals themselves and confirm if the minerals we hope we're making are indeed the ones we're making, because minerals can be a bit tricky to control sometimes. And then we use MALDI-TOF, a version of mass spectrometry, to see if we have any of these polymers, these chains, these genes, essentially. And it looks like very much we're getting them, which is pretty exciting. And that happens at the bottom of the ocean. And usually when you think of making chains of anything biological, the bottom of the ocean is not great because water tends to break bonds. So if you put genes on water over time, you're going to break these genes into individual building blocks. And what we're seeing here is that under these conditions, the building blocks self-assemble into genes, which is pretty exciting. Another kind of origin of life project that we're working on It's more on the kind of evolution path. Instead of making organics, it's okay, let's assume that now we have these organic molecules. These are known as amphiphiles, or in this case, we're using a mixture of fatty acids and phospholipids. These are molecules that are like soap, essentially. So one side of the molecule is nonpolar, these kind of long tails, these tails here. And then the other side of the molecule, the red stuff, is polar. It likes water. So when you have these molecules that we assume could have been made, we're not making them in this project, we put them in water under XYZ type of conditions, and then we see under this which conditions they make these protocells. They kind of self-assemble into a compartment, essentially, a closed protocell. Usually they're going to break down depending on the conditions, but now we're studying under which conditions they divide into daughter cells. So for example, if we shake them under the right conditions, right salinity, they're going to break down into kind of daughter cells. So we are thinking of this as a very crude and basic and not very advanced, but still happening way of replicating the systems, where you go from 1 into 2, 3, and it's an exponential buildup. And that's cool, but usually that wouldn't be so important on itself, because this system, you know, it's not adapting to its environment. So we're interested to see if the composition of these vesicles, these compartments, if you have a population of different compositions where each one of the vesicles has a different phenotype. Essentially, some of them may be best suited to living across higher temperatures or lower pHs. So basically what we do with these vesicles, we make them, and they are all very different. They have like strengths and weaknesses. We stress them, and then we see which ones survive. And then we try to make the ones that survive go into the next generation and see if the daughters are going to inherit these capabilities. And that is a super basic form of evolution. It's super basic, okay? So if you're a biologist, you'd be like, no, that's not evolution. But we think that that's a proto-evolution, if you will. So we do this using microfluidics. So again, these tiny chips where the reaction volumes is in the microliter or nanoliter scale, so tiny, tiny stuff. So we need to use these chips, for example, and here you can see these little vesicles forming. You can see these little dots. Each one of them is a vesicle. And then they go into this chamber where we separate the vesicles from all of the oil gunk that we have. And then once we have these vesicles, we connect this to another chip where we're going to accumulate them, stress them, and basically make their lives a little bit of an ordeal. Once that's done, we use fluorescence microscopy to study what they are made of, and then be like, okay, the ones that survive are made more of amphiphile A instead of amphiphile B. That means that under these conditions, so basically we can keep track of lineages of like how this, basically it's like building a phylogenetic tree, a tree of like relationships, but with these systems that are just made of fat, okay? And finally, we have another project that I'm not gonna talk too much about that, but that's what the new postdoc that we're hiring is gonna be working on. And that's working together with our director, Patiferia, who works a lot with tropical diseases, and Tian Dong. And Tian Dong used to work here with Tim Gouge at UT Austin. So maybe some of you know him. And he's worked with Mars a bit. I haven't. But now we're going to start working on Mars, and we want to use the Rio Grande Valley, which is a river that, because of our huge droughts, essentially, it's becoming drier and drier, a bit like what happened to Mars back in the day, for very different reasons, probably. But we want to see how we can look at biosignatures, basically remnants of living things, and how they get affected by these riverine dynamics and deltaic deposition. Essentially how they change location, and also whether the different areas where they get deposited, if they get preserved, or the place where they are happening, the minerals and the depth, etc., changes them. So do they become essentially biosignature diagenesis, how these biosignatures change over time. And the main reason we do that is because that's an image of Mars. I think that's in the G0 crater, but it could be Gale, don't quote me. But essentially what we see here is a deltaic fan. So these structures are very well known and studied in Mars, and we have some rovers around there right now. So we want to use the Rio Grande Valley as like a Mars analog, which, you know, for people that work in Mars, it's sacrilege to say that, but we're getting started. We'll see. We'll see what happens. So this is a little bit about what we do in the lab, other than the two projects that we'll talk about later. So I don't know why I added this, because I'm talking to an audience of people that cares about planets anyway, but usually I give this talk or similar talks to people that are on the chemical side or on the biological side. And to them, when you talk about to them about planets, usually they don't quite get, like, who cares? They're just like these balls of rock or not in space. So they don't grasp how, even for biologists, how important Earth as a planet is for life, and vice versa, right? And habitability, and how life makes Earth more habitable as well. So to me, I see life as a planetary phenomenon. So life probably can only start in the way we think of life in a planet or in a planetary body. So maybe a moon is also fine. I don't think that life can start, for example, in a meteorite, because it's not a planet. It's not complex enough. So that's kind of where I'm thinking. So if you want molecular complexity, which is a requisite for the origin of life, you need a complex environment. And a planet or a planetary body, it's at least some of them are going to be complex enough where this chemistry can like basically become self-sustaining and evolve for billions of years. It is interesting to consider that, you know, I teach astrobiology for undergrads and grad students at UTRGV. And what the first thing I tell them is, I want to change the notion that you live on Earth, because you don't live on Earth. You are Earth. You are a part of Earth as much as the atmosphere, as much as that chair. You are Earth. And the reason for that is that all of the matter, or the huge majority of the biosphere, of the matter from our planet that is the biosphere, was here when Earth was formed. It's only a small amount that has been delivered, that it actually makes it into our bodies. So that's, you know, that can go into like some strange areas of Earth and planetary sciences with the Gaia hypothesis, right? And I don't want to become too new age here. But I think it's interesting to think that indeed a biosphere is not just on a planet, but it is that planet, right? And if you push that even further away, you can think of, if life moves from planet to planet, and of course we will be able to do that very, very soon when we colonize Mars, which is going to happen eventually. But even if it's not just with technology, right? We suspect that there's this, probably some of you have heard about the panspermia hypothesis, where life goes from planet to planet naturally with like something known as a planetary meteorite, right? Where a meteorite strikes a planet at the good angle, where you dislodge some rocks from the original planet. These rocks float in space and then crash on another planet. And some organisms may be able to sustain and like live through that. If so, you can have life going from planet to planet. And in a way, if you're in this weird kind of point of view, you can think of life as being the way planets reproduce. Because if we colonize Mars, a little bit of Earth has now copied itself into Mars. Just think about it. It's a bit weird, but most importantly for a biologist, I want to understand why life seems to emerge in some planets, but not in all planets. And what are the conditions, the boundary conditions, like almost like a phase transition, right? We have phase transitions for minerals, and why under this pressure and temperatures, life is, this mineral A or mineral B is going to form. But we don't really understand the phase transition or phase transitions of biology. Why under some conditions, this geochemistry is going to become biochemistry. I really want to understand that. Again, I don't need to explain to you how planets form. They form in protoplanetary disks. You know this. I think this is a really pretty real protoplanetary disk that was imaged a few years ago. And of course, then in these disks of materials, planets will form by planetary accretion. I know that there's a lot of controversy on whether this happens with these big boulders or these tiny pebbles now, but I don't know enough, so I don't know if some of you are accretionary people, but I'm not going to talk about that because I'm scared. But something that, of course, then happens is if you have, for example, a rocky body where you have all of these molten materials, once the planet starts cooling down, you're eventually going to undergo chemical differentiation in layers where you have more denser materials falling into the interior and less denser materials floating on top, and essentially making something for Earth that looks, by like early to mid Hadean, after a planet collides with Earth and forms the moon, you have more or less a pretty much planet that if you make a cross-section would look very similar to the modern one. Even though the dynamics would probably have been a little bit different, the structure is pretty much set. So when I think about the origin of life, I always think, even though it looks as if what I'm doing is chemistry, in reality, I'm doing a lot of physics, because what I care about is energy and energy transformations. So, and understanding bioenergetics, how energy travels through a cell, is very important to understand, well, life in general. So growth, illnesses, essentially, the only thing we need is a source of carbon and a source of energy, okay, to like be self-sustaining, even though we're not self-sustaining because you need energy. But energy is central to understanding biology. So if energy is central to understanding biology, I think that it's also very important to understand energy flowing through a planet to understand how life starts in it. So, this is geophysics, so I don't need to explain the laws of thermodynamics to any of you here, but the universe is tending towards equilibrium, planets including. So planets, when they form, are full of energy, not just in the form of heat, but also in the form of heat. So essentially, they need to lose this energy and dissipate it back into space or into achieving closer to equilibrium, right? Second law. But we do see some complex phenomena emerging in a universe that tends towards this equilibrium. And that was very puzzling for many years for physicists until Eloi Prigogine, back in the early 20th century, he proposed that life is nothing more than a very complicated, but nothing more than a dissipative structure. So that in the same way that a hurricane forms in a planet because of a thermal gradient where you had hot air meeting with cold air, and that generates this non-random pattern ordered structure that emerges because it dissipates energy, in this case, thermal energy. Eloi Prigogine proposed that life is also a planetary phenomenon that dissipates energy. It's just that it's a different type of energy. In this case, it's mostly redox energy. There's also photosynthetic life that dissipates light coming from the sun. But we think that photosynthesis is a bit of a later invention of light. It's a bit controversial, but that's more or less where the consensus is. So we see life that was chemotrophic, life where the energy that they get is between the reaction of two chemical species. That's basically like us, okay, and many cousins. So basically the energy that life dissipates is the energy between one molecule that is rich in electrons, an electron donor, and one molecule that is poor in electrons, an electron acceptor. In our case, we eat burgers, or in this case, I did this graph when I was in the Netherlands. So these are bitterballen that you eat when you're drinking beer. And then we breathe that with an electron acceptor, which is oxygen. But if you're in the early Earth, you're going to do this reaction, which is what methanogens do. And they produce methane. And this reaction releases energy. And so these organisms, us or these methanogens, are also destroying or dissipating this energy gradient, in this case, in the form of redox disequilibrium instead of thermal. So that's how I see and think about the origin of life at a planetary scale, because we think that in the origin of life, there was big amounts of hydrogen being produced in the mantle/crust and big amounts of CO2 in the atmosphere. So you have a planet that is essentially a giant battery, a very negative crust full of electrons and a very positive atmosphere depleted of electrons. So this giant battery in volts essentially can produce life. In other words, producing life by this planet is a way of getting rid of this disequilibrium. So a planet, if it can, will promote life's emergence. That's like the big picture. Then how you make that, how you prove that in the lab, it becomes difficult. But that's the point. of course, we look at signs of life using atmospheric disequilibria for exoplanets. So some of you I know work or are interested in exoplanets. It's not what I do, so I don't want to talk too much because I don't know enough. But it's important to understand that Earth's atmosphere has changed dramatically over time. The atmosphere of Earth and of other planets, we think, changes quite dramatically depending on the rate of maturity of the planet, and also if it has life or not, and which type of life it has. So for detecting life beyond Earth, this is also very important to understand how the atmosphere changes over time. We don't know exactly where the origin of life happened on Earth, but we think it was around early, so like probably around the Hadean or very early Archean. And then this is how oxygen has changed on Earth over time. We have here the Great Oxidation Event, and then a second rise of oxygen after what's known as the boring billion. Problem is, we don't have rocks from this period because plate tectonics is great for making Earth habitable, but it's constantly destroying ancient crust. So we just don't have any of those rocks. We only have some zircons, tiny minerals that tell us something about that, but we don't have actually big rocks from that period. In fact, we do have one rock from that period. We have a few more, but this is the biggest one that we have, which is known Big Bertha, that was collected on the moon. And it's a planetary meteorite from Earth that landed on the moon. Thanks God for that, because then the Apollo missions recovered it. So we can study a little bit of an old Hadean. So that's like 4 billion years old. So from here, that if it was on Earth, it would not have survived. But it did survive because the moon doesn't have plate tectonics. So thank you, moon. But it's not enough because we only have a handful of these samples. So we still need to use plenty of modeling to reconstruct how the atmosphere looked back then. Why do I keep talking about the atmosphere? Who cares, right? It's just gases. And you know, if they are these gases or those gases, why does it matter? Well, it matters a lot because mostly the redox state of the atmosphere, how rich or poor in electrons the atmosphere is, will push or make or prohibit certain types of reactions for the origin of life. So if you have a reducing atmosphere, which is the atmosphere that Miller and Urey simulated when they were doing this famous, in the 50s experiment, the Miller-Urey experiment, where they took this very reducing, highly rich in electrons atmosphere, they put some lining and then amino acids, which is the building blocks of proteins, came out. They were like, look, origin of life is solved. Of course, now we know that's not great because we heavily suspected the atmosphere was not that reducing. And also, even once you have just amino acids, that doesn't mean that those things are going to come alive. In fact, amino acids are everywhere in space. You find them in every single piece of rock material in space has amino acids, and that doesn't mean it is related to the origin of life whatsoever. But it was very important at the time because it was the first time that organic molecules that are biomolecules were made without using any life. So at the time, it was extremely revolutionary. But we now think that these gases are not realistic, that the Earth's early atmosphere would have not been so full of electrons. And it's kind of cheating because organic molecules are reduced. So if you start using building blocks, these gases that are already reduced, you're kind of halfway there. So if you start with gases that are much more oxidized, it is significantly harder to get organic molecules. So it makes sense that they did that because, you know, as good synthetic chemists, they knew that if you start with already halfway there, you're going to get there faster. But was the atmosphere oxidizing or reducing? That's the big question for the early Earth. And probably it was like somewhere in the middle because there was no free oxygen, we don't think. So it was not as oxidizing as today, but probably it was also not as reducing as you can see here. So how do we study the level of oxidation of this early atmosphere? Well, that's what we have been working on with Anders Johansen, who is a planetary geophysicist in Copenhagen, in Globe Institute. So he got in touch with me and was like, hey, do you want to be my origin of life guy for this paper? And I said, yes, because I want to understand things about the early atmosphere. So I got to learn a lot. So we basically make it into our goal to understand what would have been the amount of not just CO2, but mostly CO2. How much CO2 would have been present in the early Earth atmosphere? So you know that whenever you are rocky planets like Earth undergo most likely two types of atmosphere outgassing. The first one immediately when it's cooling off, and you get a lot of hydrogen and helium, but then all of this is, for the most part, lost to space. because of solar sputtering and just simply Earth is not big enough to hold onto those gases. But then you have a secondary atmosphere that outgasses from mostly volcanism, okay? So the question is, okay, once you are in this stage, which happens relatively fast, what are these gases going to be stable in the atmosphere? Because it's not good enough that you're outgassing these gases, they need to become stable in the atmosphere. So this is a paper that was published about a month ago. So I encourage you to go and have a look if this is interesting to you. We care about basically building this model that tells us what would be the redox state of the atmosphere. And then the origin of life angle to it is understanding if the atmosphere is more oxidized or reduced, which forms of fixed nitrogen, that is nitrogen that is not in an N2 form, which is pretty much inert, is going to form. So if we have an oxidized atmosphere, you're going to have different types of fixed nitrogen than if you have a reduced atmosphere. So we quantify the degree of oxidation of the atmosphere using this number that we kind of make up, RO, which is basically everything divided by oxygen. So the smaller the RO, the more oxidized the atmosphere is, and vice versa. And this model makes these kind of three main types of atmospheres. And our job was then try to figure out which one will be the most stable. And that is depending on the rate of oxidation of the whole planet versus the rate of CH in the mantle, essentially. So to understand which one of these three atmospheres, right? So this one is going to be extremely oxidized, it's going to be extremely reduced, and then this middle ground where it is dominated by water and CO2. And spoiler alert, this is the one which the model predicts is going to form. The main reason that happens is because of this reaction known as the water gas shift reaction, which we can see here, where CO and water react and make CO2 and hydrogen. Here, there's no real oxidation or reduction going on. Well, it's both, right? CO becomes oxidized and water becomes reduced. But then most importantly, this H2 is going to escape to space. So what you get is a net gain in CO2, which oxidizes the atmosphere. But what we wanted to know is how fast does that happen? Will this take a whole billion years, like the whole Hadean, or will this happen in just a few thousands or millions of years, which means it's pretty much instantaneously, geologically speaking. So the model, it's kind of, don't have time to go too much in depth about that, but basically we model how oxidize or reduce the iron woostite buffer would be. So the gases coming off, would they be more oxidized or more reduced? And it depends, right? We don't really know how oxidizing the Earth mantle would have been. And there's papers for everyone, so you pick your poison here. But what we think is cool about our model is that it predicts that regardless of the oxidation state of the mantle and then of the atmosphere, so whether you're much more reducing or more oxidizing or bang in the middle, the atmosphere will inexorably be dominated pretty quickly by CO2 and water, which in other words, it means it's a mildly oxidizing atmosphere, but it's much more oxidizing than what Miller-Urey did. And in this case, it happens almost immediately where water and CO2 will become dominant in the atmosphere, and you have reduced gases like CO2 and hydrogen just going into zero pretty fast in just a few million years after the moon forming impact. And if you take into account some of the kinetics of ammonia and methane, which some of the reviewers pointed out, this thing still happens. It's just that it takes a little bit longer for CO2 to dominate, but it's still just a few million years. So what our model says is that regardless of the level of oxidation of the mantle, you're going to go into CO2 domination extremely fast. And the cool thing is that this should happen for any planet that is rocky. So our prediction is that exoplanets that are rocky, size of Earth-ish, should also be dominated by CO2. And we can falsify that by looking at what data says. And so far, the two planets that we have seen, one is fully dominated by CO2, astronomers say. I'm not an astronomer. And the other one has significant amounts of it. So we think that the model is not too wrong. So then we looked at how fixed nitrogen would happen. We care about that because right now on Earth, we have fixation by lightning, life, and industrial processes. And the origin of life, none of these are there. So it's only lightning, essentially. So we had a look at how efficient the atmosphere that is dominated by CO2 would be at making fixed nitrogen by lightning. So we make these atmospheres that go from oxidizing to reducing. And then we look at how the amounts of NOx species, basically nitric oxides, versus HCN, which is the holy grail for prebiotic chemists. So if you are familiar with the RNA world, people love HCN a lot, okay? But we see that HCN, this reduced carbon and nitrogen species, is only formed in reducing atmospheres. And in atmospheres where RO is equal to 2, which is what our model predicts, which is mildly oxidized, you're not going to form almost any HCN. And instead, you're going to be forming these other forms of fixed nitrogen, which is NO and NO2. What it happens with this is that we think that then this dissolves into the ocean pretty efficiently because it's a polar molecule. And then in the ocean, it can be taken by deep sea hydrothermal vents and be transformed into ammonia, which is the way that biology uses nitrogen. So I don't have much time to go in depth on here and why this matters, but in Origin of Life, there's like these very different schools of thought on whether we should use this molecule to build the building blocks of life or this molecule to build the building blocks of life. Our model says we should use these ones. Although there's some caveats there. Some people say that if you have a big enough impactor that brings a lot of reduced metals, you could have for a few millions of years an atmosphere that it's transiently reducing. So during those millions of years, you could produce still plenty of HCN by aligning. But then eventually the water gas shift reaction would shift the atmosphere back into the default state, which is oxidizing. So we're not solving anything here, but we're explaining what the default state would be, which is oxidizing. And those are the conclusions, but I don't have time to. So I'm just gonna, in 1 minute, gonna talk about the other kind of ocean world project that we have going on in the lab, which is to understand what's going on at the surface of Europa, this moon of Jupiter. So we think, we as in people that know more about geophysics of ocean worlds, we suspect that in the bottom of the ocean of these worlds, there's probably going to be these chimneys that on the early Earth, they might have had to do with the origin of life on Earth. So it's pretty exciting because if these submarine hydrothermal vents are present in Europa, maybe an origin of life has taken place in Europa. And even if not, it probably suggests that that planet or planetary body is habitable. So when we send a probe there, and we are doing that, we need to be very careful not to seed it with our own life, as I said earlier. Oh yeah, and that's like a cut of how it could look. Now Europa Clipper is going to tell us more. Europa is an ocean world because around 16% of its volume, it's liquid water, whereas Earth is like 0.12. So Earth is a dry planet, even though we think of it as like a very water-rich planet. We're nothing compared to Europa, or like Titan, for example, 26%, or Ganymede, 46% of water, right? Those are proper wet worlds. So how do we work? So yeah, that's old news. We know the Clipper is going there. So this is a NASA grant that was funded in my lab, and essentially we care about understanding what the organics that we find at the surface, where do they come from? Do they come from exogenous delivery by meteorites that carry on a lot of organic materials, or some of it comes endogenously from organics being made in the ocean or ice-ocean interface or rock-ocean interface? By biology or not, okay? So here, so far, we're not differentiating between organics made by a biosphere or organics made by farting rocks. We don't care yet because it's complicated. So the project is about differentiating between endogenous organics and exogenous organics. The way we're doing that is essentially simulating mostly exogenous because we know much more about the organic composition of rocks in space, of comets and asteroids. And then we are already simulating what happens when we simulate these radiation conditions. So when these organics become irradiated by the sun, do they change in some way? Because the organics delivered are XYZ, but then over time they mature because of these high energy conditions at the surface. And we don't really have a chemical map on how they change, but NASA needs that to interpret the data that we get from Clipper. Because otherwise we will not know if these organics that are not exactly the ones from space are the ones from space that have changed or are indeed from the interior. So our data is going to be able to help differentiate between organics that came from space versus the ones coming from the interior of Europa. At least that's what we want. So in the first 2 years of my tenure track position, which have just finished, I dedicated to build this little guy, which we call Boreas, because marketing and, you know, some mythological fetish. And then, so basically it's a vacuum chamber that puts the pressure down there into like interplanetary pressure. So like real low, we have then this light source that is basically, it's a xenon lamp that simulates this light of the sun. Then we have here a helium-powered cryocooler that pushes the temperature down to minus 200 degrees Celsius, which is what we need for that. And then essentially, we're just making ices. Here you can see this kind of copper breakfast waffle where we put these ices in there, and then we irradiate them with a light source. And now we are starting to use a combination of LCMS, NMR, Raman to understand bulk chemical changes. So if we get, for example, amino acids, do we form under X amount of radiation? Do they break down into CO2 and ammonia, for example, or not? And what happens if we dust this with like some dust from Io, a nearby moon that is volcanically active and release a lot of sulfur? Do these change these chemical pathways, etc.? So that's what we're working on, and that's it. I'm late enough. Thank you. Oh, that's cool.
Thanks, that was really interesting. I was wondering if you could talk about, like, do you think the plate tectonics is like a necessary condition? And then how do you sort of square uncertainties in the origin of life, timing, and the origin of plate tectonics?
Necessary condition, that's a great question. Thank you. For the origin of life, or for habitability, or both?
Maybe specifically life.
Right. We think that during at least half of the Hadean, there was not modern plate tectonics, so where plates move horizontally. Well, we think, I'm not a geologist, so I'm sorry. You know more. But I've read that most likely it was not this modern regime where they form, you know, in like mid-oceanic ridges and then they travel horizontally, but it was most likely some sort of vertical floundering, like a lava lamp, right? Where by temperature, you just have these big slabs falling down and then some others going up. But I think that some form of crust recycling is important. Because otherwise, if you're in a Mars type of scenario or like stagnant Lee type of planet, in a geological like billion timescale, essentially, eventually you will run out of food. Particularly if your surface is nasty, as Mars is. So I think that if there's, for example, some life on Mars, it will have been very lucky to survive in these kind of pockets of like kind of more or less recent volcanic outflows, where that is the only way of bringing new materials back into the surface. But I do think that for habitability, plate tectonics is very important. For the origin of life, I don't think so. It's controversial, because I think the origin of life is something that happens fast, or it won't happen. Fast means a few thousands of years, probably. Because biology is, I don't usually like this origin of life scenarios where you have these chemicals accumulating over thousands of years, and then eventually they reach this critical mass where they will eventually react. Biology is not about that. Biology is all about fast reactions, metastable. So I don't have any reason to believe that the origin of life, biology, would have been less stable than it is now. Probably would have been more unstable, AKA faster. So I think if the conditions are right, life will spring on. It could be, though, that if there's no crust recycling, that life will become extinct, though. So I think crust recycling is important for habitability, long-term life being viable there. For life starting, I don't think you need that, because back in the Hadean, the crust was new, so it was recycled by default. And I think that would have been a pretty fast process. But that's only my opinion, and, you know, take it with a pinch of salt.
Thank you.
For the first experiment that you're currently doing with the bilayers, are they phospholipid bilayers?
Yes.
Okay, so for the phospholipid bilayers, what differentiates them? Because you said you had many types.
Yes.
Is it like integral proteins?
No. We want to do proteins, but not yet because it's
Okay.
already too complicated. So initially we started working with fatty acids, which are smaller and more prebiotically plausible because, you know, smaller molecules are easier to make, but they hate to exist. And it's fine. It's more realistic. And eventually we want to go into fatty acids. But we found that the way we torture our molecules, we needed some vesicles that are more sturdy. And we use phospholipids as a proxy because it's easy to make vesicles, and they are going to be somewhat resistant. So we can torture them with pressure, pH, temperature, and they don't just explode immediately. And then we are basically using different types of phospholipids. Right now we use two. One is a phosphatidylcholine and the other one is a sphingosine. And we use them because we want them to be chemically different so that the vesicles they make are also, so they are chemically different, making vesicles that are physically different. And we want that because for evolution, one of the prerequisites is natural selection. But on top of that, you need the individuals that will be selected for to be different. So we need to make vesicles where every individual, more or less, has a different phenotype, has a different fitness. So some should die easier and some should not die as easy. And that is basically gonna select the fit ones. So that's why we use two, and we wanna use more, but it's just that every time we add another phospholipid or any other amphiphile, the model, because we're also building a model, becomes much more complicated. So we're like on early stages of this. I don't know if I explained right. And also we need to buy fluorescently labeled versions of them. And also we're kind of constrained about which ones the companies sell them already labeled. So we cannot just use whatever we want. Yeah, we're kind of, they are expensive, so grants. Thank you.
Hey, thank you for a exciting talk, and I really like the rig that you have to actually create DNA synthesis on abiotic condition. But however, I would reframe it as this: there is a debate on what is life. Life has to be reproduction.
Agree.
It has to have a metabolism. So I would say that it is the origin of the chemical life. Now, that's great,
I agree.
but it doesn't say anything if it could survive in a prokaryotic cell and pass through the transcription and translation. So I was wondering if you can take that DNA that you synthesized already, use CRISPR to put it in a prokaryotic cell, and then expose it to the extraterrestrial conditions and see up-down regulation of microRNA. And then you would see if that cell can survive, if it's compatible to prokaryotic cell. Because a good metaphor will say, you know that somebody started a marathon, but if he didn't finish, there is no life. There is just a chemical.
Exactly.
So I was wondering if you're doing top bottom using microRNA.
I think you're totally right. And probably I will die and not my lab will have made a living thing from scratch. So we're basically just, you know, in a long marathon, as you say, this is like a relay distance of like 100 meters. And yeah, even if you have like, I'm not an RNA world person, even though I think RNA is very important. Yes.
Extreme conditions, but it doesn't say if we can pass through the cell, through the membrane, and produce. So that's a different thing.
You're totally right. So I like what we call metabolism first, where we don't think you have one molecule like RNA that is going to be the catalyst for every role. So in my mind, this RNA, it's another piece of the puzzle that will inevitably arise, and eventually it will. We don't know exactly how or why it would take the role of like storing information in the form of DNA eventually, okay? But we basically work in this scenario where you have chemical autocatalysis, where many chemical networks are all self-reproducing. So a bit like the Krebs cycle, I don't know how familiar you are with that, where every molecule itself is not replicating itself, but because it's part of the network, the whole network doubles in size. So in this mindset, RNA to me fits in there as like something that is going to be very important, which itself will be a catalyst because a lot of these cofactors in biology today are little dinucleotides that they, for example, chelate magnesium and they're going to do XYZ type of reaction. So, but yeah, this is step 0.01 out of 3 billion. I agree.
Good throw though. So talking about the early Earth and its atmosphere, it being less reduced, what would that potentially mean for the oceans? Because I know there's been some discussion that the ocean oxidation for the Great Oxidation event was potentially later than the atmosphere. And so if you had your very reduced atmosphere that, maybe then became less reduced, what would that potentially mean for the oceans? And have you looked into that at all?
No,
Okay.
but we can. We should, maybe we should do it. Yes, no, I don't know almost anything about ocean dynamics, but yeah, you're right that whenever there was the GOE, it took like 1 billion years-ish for like the whole ocean until the depth to become oxidized, right? We had this like weird oxidized and ferruginous eventually. Yeah, so I remember that from here. Probably something similar happened, but yeah, I don't really know. Well, CO2 dissolves very easy in water though. So I have the feeling, but I know this is like kindergarten fluid dynamics, is that it would have been faster than like oxygen dissolving in water, but maybe not. Correct me. But I don't know how fast. And for us, what the most important part is the NOx species. So once you have these nitric oxides, how easy it's for them to dissolve into the ocean, and then through this circulation, through the hydrothermal, like the bottom of the ocean floor, and then through the vents, react with hydrogen from serpentinization, become ammonia essentially, and then become available for prebiotic chemistry or life anyway. We're winging it. There's some work done by Yuk from Caltech and Mike Wong, who's now in Carnegie Planets, I think, and some people that worked on that. But yeah, I don't know how realistic those are and how much we know about the depths of the ocean and currents. But it is something that we need to figure out. Good question, thanks. Do you read it? I can see it. Oh, I don't know if I'll see it. Where is it? Chat, okay. The recent observation of dark oxygen, oh yeah, where metallic nodules from the ocean can cause water electrolysis generating hydrogen and oxygen. Do you think a similar system could have influenced biogenesis in the oceans? Perhaps, but I am skeptic about oxygen as in O2 being part of abiogenesis, the origin of life, because so there's some people working on reconstructing ancient enzymes. So people like Batul Kasar in Wisconsin-Madison and some others, they take phylogenetic trees of genes, they take their sequences there, then they put them in a modern bacteria and makes them produce this old version of the enzyme. And all that we'll learn about early Earth organisms, so basically the close descendants of the last universal ancestor, like 3-point-something billion years ago, is that their key enzymes for metabolism are all oxygen sensitive. So to me, that suggests that at least at the last universal common ancestor level, which we don't really know exactly the timing, but it's around the Hadean somewhere, we don't know really, the enzymes were mostly oxygen sensitive, which suggests that they were not living in an oxygen-rich environment. Now, you could say, well, but that's later. It could be that in the origin of life, there was more oxygen that played a role, and then because it got reduced for XYZ reasons, then they adapted to not using it. And I say, it's not impossible, but it requires 2 explanations, and I usually go Occam's razor. Because early life does not seem to use oxygen. To me, it makes more sense to assume that the origin of life also did not. But it is hard to prove one way or another. Thanks.
Let's say thank you to our speaker.
Thank you.
And there will be lunch for students and postdocs. So I think I told Perry that she should be in charge, but I think she's arriving a little bit late because of her dog. So yeah, I think that'll be I think usually you guys meet at 11:45, right? Yeah, in the lobby. And yeah, thanks so much.
Thank you, guys.
Oh, and a reminder that we still have a couple spots open for dinner tonight at the Peached Tortilla. So if you would like to get dinner tonight with our speaker, please sign up on the spreadsheet that's been going around. Thank you.